You don't have to have a copy to perform what I want you to perform. I want 3 things. Clearly, I want the answers to the questions here. I would like you to sketch a velocity versus time graph, but I would also like you to sketch a position versus time graph. I want you to do all 3 of those things. And I think that should take you roughly 120 seconds, 2 minutes. So I'll give you 2 minutes to complete it. If it's already done, great, move on to number 2. If you've already done number 2, move on to number 4. That's where it starts to change. Okay? 1, 2, and 3, they're all the same. 4 is where it starts to change. So I'll give you 120 seconds.
I picked the back part of the paper, and they picked up like front part of it. Could we get can I get the front part as well? Does that make sense?
Well, I wasn't going to print anymore, but
Thank you.
they'll be over there at the printer. All right, so that's about 2 minutes. Your graph, the first one, pretty straightforward. Looks like mine. Then we, did you find the area? And what did the area tell you? I mean, what is that? When you find the area, what are you finding? Say it, I'll call. Displacement's fine. So area is 175 meters, correct? So you should have found, of course, that the displacement of the car is 175 meters. How did you find the acceleration? What other property did you use? The slope. Slope would give you the acceleration. What was the slope of this graph? So it's 5 minus 20 divided by 5? So that's 6, right? I don't think it's 7. 6, yeah. Yeah, 30 divided by 5, still 6, right? Just checking. All right, so slope would be 6. Let's be careful. It's a positive slope. Acceleration is a vector quantity. And just like it's a positive area, displacement is a vector quantity. So it would be best to make sure we are aware that we're dealing with positives here. Now, even last night, I was fielding questions about how to deal with your position graph. I really want to move past this. I want you to be good at it. But I don't want to spend a lot of time on it either anymore. We assume the object starts at the position of the origin unless we are told differently. So we don't know where the starting point is just from looking at the velocity graph or just from our problem. The problem itself doesn't say where the object is at time 0. So we assume the origin. And at time 0, the object's velocity is 20 meters per second. So at time 0, I have a positive slope. I'm not sure how steep to make it, except I know I want to take up a lot of the graph paper here. So 20 is a scale based on what your graph is. I'm saying that because at 5 seconds, I'm going to try and use a whole lot of graph paper. I'm going to put my dot over there someplace to indicate that after 5 seconds, I have moved in a positive direction, 175 meters. And at this moment, my velocity should be 50 meters per second, which means the slope of the position versus time graph should be positive and steeper than where it was when it started. Can't really do 50 or 20. I don't have a scale for that. But I know it's steeper because 50 is a bigger number than 20. And now, understanding that my curve is going to become more steeper As time goes on, I need a smooth curve that would connect the two data points together to indicate I understand that the object's velocity is increasing. The position graph tells you a little bit about the velocity too. What you are seeing here is what I'm expecting tomorrow a bit. Any questions about this? Yes, sir.
How did you get 175 meters?
I did 1/2 sum of the bases times the height. This is a trapezoid, so this is base 1, this is base 2. Base 1 is 20, base 2 is 50, height is 5. So 1/2, 20 plus 50 times 5, 20 and 50 is 70, 70 times 5 is 350, 350 divided by 2 is 175.
Thank you.
You're welcome. Yes, ma'am. I think that might be a good idea. But if you follow along with today's discussion as we progress, you might find that that is time wasted. You'll see if you pay attention. So if you don't know the area of a trapezoid, yeah, get that into your head. Memorize it. It's not on your equation sheet. So I would like you to have it. But we're using that in a few minutes. And what we're going to produce from that is more important that you memorize. So you'll have to make a choice perhaps on the number of things your head can store. Can I move forward? Do we need to do another one like this? I'm afraid we probably should do number 2, only because I know some of you will screw it up. And I don't mean that mean. I just mean if you haven't done number 2 yet, it's enough different where if you're not careful, you'll screw up the position graph. It's not a hard one. So 60 seconds, try and do the position graph for number 2 after you sketch the velocity graph. This one's easy. Time on this, I feel like you should be practicing already. Was this one too terrible to expect you guys to do like one of those and put 6 here? Any question about that? All right, so positive 9 meters. Did the area there, right? Just triangle, 1/2 base times height. Again, starting from the origin, after 3 seconds, it had moved a positive 9 meters. This is what separates you guys who know what to do here and you guys who don't. And I know some of you have this wrong. And some of you didn't do it because you're still confused and I didn't walk the room. But it starts with a velocity of 6 meters per second. So that is a positive slope. I'm looking at this point and using that to consider the slope here. Positive. Steep, I don't know. Steeper than where it's going for sure. Because after 3 seconds, the velocity is 0, which means a slope of 0 here. So I'm expecting it to look like this. And I know I have people out here who have one of those. I know it. And you're wrong. Figure out why you're wrong. So concave down. It shows that the slope is continuously getting more flat because the object is slowing down. There will be problems in the multiple choice that will have blank graphs. They'll look just like this. They'll be super simple looking. Stuff like that, just stacks of them. A through H, every possibility. And then there'll be a variety of questions asking you to pick out which one represents some kind of motion. Or pairing them together. Which one is a velocity graph that would go with this position graph? And they'll just look blank like this with the expectation that you can kind of fill in the blanks on what it is. So most missed question on a first test will be these. Need to add, so this is all yesterday's work. So adding today. Ready? So far, we have discussed 5 things. It might not be obvious what we've discussed. Ooh, my handwriting. So I kind of want to summarize it. These are the 5 variable names that we have been discussing. We haven't used these words, but we've been kind of alluding to them the whole time. There's been a starting velocity and an ending velocity for each of these intervals. So we've been alluding to them, but not really talking about them. I'm giving you formal words I wish to use in class. More importantly, I'm done with saying base and height and trapezoid and all that. It's not really useful. These graphs refer to things. They refer to positions and velocities and time intervals. So although it's been nice using shapes like trapezoid and triangle and rectangle, that's really not the direction we need to go. We need a bit of an abstraction here. These represent things that are happening. So I want to use a certain amount of symbology in this class. And this is the symbology I've chosen to use. Displacement is change in position. Because it's change in position, it has a certain symbology that should be used to represent change and position. We'll use the lowercase x for position right now. The bar on top signifies that displacement is a vector quantity. When I put the bar there, I'm reminding you that you should consider direction as part of your answer. When you give an answer, like in a few moments ago, 9 meters, it should be 9 meters in the positive direction. 9 is just 1 out of 3 points for your answer if you think about it all the way. 1 point for the number 9, 1 point for the direction, and 1 point for the unit. So if it's a 10-point question and 3 of those points are about how you state your answer, be aware, without the unit, you're losing the point per answer. Without the direction, you could be losing a point per answer. And I'm not making this up. This is how AP is going to do it. So every one of these never has just a number for the answer. They're all going to have a unit and likely a direction. The only time that's not true is if they ask for the magnitude of the vector. That word is often new to students, and I'm not writing it down. The word magnitude means size. Whenever you see the word magnitude on anything that I type and hand to you or any test from AP, you can scratch out the word magnitude and write the word size. If you don't like that, it's the number part. If they say, what's the magnitude of the velocity? They just mean put 5 meters per second. If they say, what's the velocity? 5 meters per second in the negative direction, 5 meters per second upwards, 5 meters per second north. Give it a direction, whatever the directions are that you've been using. Initial and final velocity, I've decided to use VI and VF. They are using that again this year on your sheets, so I will continue to use them. They are vectors. Initial velocity in your definition should be the velocity at the beginning of the time interval. Okay? Final velocity is the velocity at the end of the time interval. Acceleration we discussed yesterday. It's the rate of change of the velocity. I'll use an A with a bar on it. And time is not a vector, time is a scalar. Although, for you guys who are actually interested in science, look up time's arrow. It is believed by most physicists and scientists that time does have a direction, that things occur in a specific direction. Otherwise, it violates the second law of thermodynamics. It's an interesting read if you're really a nerd like me. It might not be interesting to you. Generally, meters per second squared, and seconds. Now, the reason why I want to do this is I want you to read question number 4. 4 changes the script a bit. All right, so we all have number 4. A runner starting from rest runs 100 meters in 10 seconds. We're assuming he's accelerating. Can you draw me that graph real quick? That one should be cake. Super easy to draw. That's about it. Can we do any more than that? Do we know where this point is? We don't. We don't know how fast the runner is traveling at the end of the interval. It wasn't given to us. What was given us? We know this area is 100 meters. That's what we know. Something I expect you could use to perhaps figure out the rest of the problem. In this case, the area was given, not the final velocity. It's just changing the parameters a bit. Could you use this to figure out the rest of this question? Try. I think that most of you should be able to do this and have an answer. I'm expecting about 60 seconds. Because I think you guys should be able to go as fast as I. It's because we've been doing this for now over a week. It's the same kind of stuff every time. I'm trying to move us towards something more useful. First, do you understand that a triangle is also a trapezoid? It was mentioned in class, but it is. A triangle is a trapezoid where one of the bases is 0. I'm saying that because it's going to come up. So I could write this as 1/2 base 1 plus base 2 times the height equals the area. But look, we know more than this. I don't have to draw this graph to know that the area of this graph was going to be the displacement. Meaning, this is delta x. It's the displacement. And I don't have to draw that graph to know that base 1 is whatever the starting velocity was, and that base 2 is whatever the ending velocity is. I don't have to draw the picture to know that. I've seen the picture 5 or 6 times even today. So regardless of the way my trapezoid is presented, this is going to be V initial plus V final every time. And yeah, there's a 1/2 here, but I don't need to draw the picture to know that this is going to be the time. That this will be true every time there's a velocity graph if, and it's a big if here, you have to understand something, what I'm about to say here, most critical part. This is always going to be true if the acceleration is a constant. That's important because if the acceleration weren't a constant, if it was curved here, that would no longer be a trapezoid and that wouldn't work. But as of yesterday, we should have a bit of an understanding that that's a trapezoid, and even that's a trapezoid. We showed all 3 of these still can be solved using the function of a trapezoid. So with that knowledge, I don't need to draw a graph every time. I can use this anytime I want, as long as I know the acceleration is a constant. This is what's known as a motion equation. It's an equation that relates the variables of motion under a particular circumstance. This is a motion equation for an object traveling at a constant acceleration. I am very careful about the way I state this. This is a motion equation for an object traveling with a constant acceleration. It's only moderately useful. I say that because can this motion equation give us the acceleration? You notice there's no a in it. So no, it can't. And even more so, it's only useful if I know 3 other things. Right? You understand, there's 4 variables in it. VI, VF, T, and delta X. 4 variables. So it will only be useful if something supplies 3 of them. Now in this problem, 3 of them were supplied. When I look at what was supplied, I have the initial velocity 0. I don't have the final velocity. The time was 10 seconds. And delta X is 100. So 3 things were supplied. If I'm careful, I could use them to figure out the final velocity, which was 20. That's just algebra. Not even algebra, arithmetic. If I wanted to find the acceleration, what have we said is the way to find the acceleration? Let me hear that word. Yeah, but something related to the graph. Yes, sir? Slope, that's right, slope. The slope of the graph. And slope is the change in the vertical divided by the change in the horizontal, correct? Change in the vertical would be V final minus V initial, right? Change in the vertical, the final value divided or minus the initial value, divided by how long it takes. Isn't that how you've been calculating slope? Regardless of how the line is, you took whatever the final value was for velocity, subtracted the initial value for velocity, and divided by the time interval. That equaled acceleration. That's what we've been doing. I don't need the graph for that. That's still going to be true as long as it's a straight line, which means as long as the acceleration is a constant, this should work. By the way, that's not a great way to write this, so I'm going to write it a little different. And there's a good reason to write it a little different. But first, I just multiplied by t, solved for final velocity. And do you note what this looks like? If you don't, allow me to help. Clearly, this tells me that if my velocity graph is a straight line, then I can use it to deal with acceleration. What's missing from this relationship? Well, no, final velocity's in it. Of the 5 things, what's missing? I'll give you another shot at it. Good job. Yes, displacement. Notice, this motion equation has 4 things in it total, but it's missing one of the motion variables. In this case, displacement. We could use this to figure out what the acceleration of the runner is. I don't need a graph for it, do I? I do need the final velocity, though. I needed to know that the final velocity was 20 in order to use this to figure out the acceleration. Once I knew that, 20 equals a times 10 plus 0. A is 2. Formalized abstraction. I don't need graphs to solve these motion problems. Apparently, all I need is the formula for the area and the formula for slope, and that will solve these motion problems. However, did you notice that the only way to get to the acceleration was a 2-step process? Did you guys notice that? That feels very inefficient to me. And luckily, you guys have had 2.5 to 3 years of algebra, so you know how to do things. So let's see if you can do something for me. I would like you to take these 2 things and find me a single function that could do the same job as both of these functions. I want you to eliminate final velocity. We didn't know it from the beginning of the problem. I want you to eliminate final velocity and produce a new function. Remember that algebra test I had you do at the beginning of the year, where this is one of the things I need you to be able to do. You said you knew how to do this. I'd use straight substitution if it were me. I'll give you 60 seconds because the bell rings here shortly. So these are the steps. Straight substitution. Combine like terms. distribute. Y'all see it okay? I need you to. I need you to see several things. First, let's do the thing. Our problem had a displacement of 100 equals 1/2 a times 10 squared plus 0 times 10. This would be using the initial information we were given to solve for the acceleration directly. 10 squared is 100, half of 100 is 50, a would have been 2. But more importantly, this created a new function that has everything in it, all of our motion variables, except for final velocity. And you're noticing, I'm starting to write these up here. There's a total of 5 of these. Each one has a combination of 4 motion variables in it. You could cheat, look in your book. You should do this instead and come tomorrow with the other 2. Right? Eliminate each of the variables one at a time until you get all 5 of these. We've done 3 of them.